Hello, I'm Martin Kendrick, an experimental thermofluids engineer, and today I'm going to be giving you a demonstration of a technique called particle image velocimetry, or PIV. I'll be using the apparatus that I use for my PhD, and that incorporates PIV, but also another technique called BOS, or background orientated Schlieren. So the way this is going to work is the experiment is currently shut down and switched off, and so I need to get everything back up and running to the point where we can start to perform a PIV measurement, and we'll get up to that stage, perform a measurement, and probably stop there where I break the experiment down and shut it off, ready for storage or for disposal. I want to start by giving a very brief explanation of how PIV actually works. So you can see there's a couple of components here. We have a camera, which is looking sort of this way in towards the board, and a laser, and this is a laser beam that comes into some sort of optics which produces a light sheet, so something like this, where we've got a 2D plane being illuminated. Now PIV was born from a flow visualization technique, and the idea was that you introduce a load of particles which move along with the flow, like so, and they would be moving with some flow, and you're illuminating them so you can see them with the laser, because these particles are very, very, very small. Now the laser, in most cases, doesn't operate continuously. It operates in a pulsed arrangement, which means it kind of goes pop, pop, and you typically have 2 pulses, and with each of those pulses you simultaneously gather an image with the camera. And so what that means is, if you know strictly when those pulses are occurring in time, or the difference in time between one to the next, so pop image, you'll have 2 images of where these particles are, and you can use the apparent displacement of the particle images and the known difference in time between those images to infer the velocity of the flow. So it's a relatively straightforward thing. Just a change in distance, a known difference in time will give you velocity. The experiment that I'm going to demonstrate PIV on is one that's looking at natural convection, and that's where fluid motion isn't being supplied by a pump or any external means. It's simply being supplied by heat being transferred from a heater to a working fluid, and in this case the working fluid is water. One of the reasons that this is a particularly tricky application is because you have this large difference in temperature near to the surface as a result of transferring heat and therefore producing density, but at the same time that change in temperature changes the refractive index of the fluid near to the surface, and so what effectively is happening is the water near to the surface is acting like a liquid lens, which is distorting where all of these particles are appearing to be. And the purpose of that other technique, background orientated Schlieren, or BOS, is to correct for that distortion so that the PIV measurements can become more trustworthy and used for validation. Another thing to mention before we actually look at the experiment is the BOS side of measurements, the background orientated Schlieren. So in addition to taking PIV images with a camera and a laser illuminating that light region, there is also a second camera used for BOS, and I'll show you how these are joined together to look at the same thing in a moment. But the BOS camera is focused on a different plane to the rear in the background, and on that plane is a printed or static background target, just a dot pattern that doesn't change. And the idea here is any distortion of the light that you see when looking through the water due to that liquid lens effect, due to that refraction, you can see that as an apparent movement or displacement of this static background target. And if you can measure that, you can correct for it. In case you're thinking that sounds quite easy, it's not too bad, but the difficulty is that the BOS target is measuring, or the BOS system is measuring the distortion all the way across the heated surface, so along the entirety of the optical length. But of course the PIV measurement is only part of the way across, so they don't necessarily experience the same amount of distortion, and so the measured distortion needs to be scaled by some amount to make sure it properly represents the distortion in the PIV images, so the images of those illuminated particles that are captured by the PIV camera. That's the difficult part of the experiment here. So here we are over at the experiment, and there's some components that might be somewhat familiar. On the left hand side we have the laser coming in over here, and behind this structure is the optics, which produces the light sheet which illuminates to the right and is illuminating the flow by this black thing, which is the heater that you see inside here. So the heater is inside a reservoir and is normally submerged under water, so this tank is filled with water. We've also got two cameras over here, so we've got the PIV camera and the BOSS camera, and the component in between those is called a beam splitter, which is a dichroic mirror. And what that is doing is enabling some wavelengths of light to be transmitted through and into this camera, and other wavelengths are being reflected up into the other camera. So both of the cameras have the same optical axis, or near enough the same optical axis. Now looking down at the heater from above in the experiment, the PIV plane that's been illuminated is here, so coming out this way. And what you can now see is this dot pattern target at the back here, which is used for BOSS measurements. And stepping away from the experiment slightly now, we can see some other components. The first of which is a cooling system for the reservoir, and so you've got 4 of these, one in each corner, and they're simply a copper coil that comes round that is used to circulate cold coolant, and that's to maintain the temperature of the water in the reservoir, so away from the heated surface, to produce a constant temperature. Something else that can be seen if we look up, there's this structure that can be moved around, and this is to introduce a variety of different targets or things into the flow, usually for the purpose of calibration. I've got a few of those things to show here. Probably the most commonly used one will be this one, and this is the dot pattern that's used to calibrate the position of the camera, so it knows how far, if it sees a pixel or a particle move a certain number of pixels, this relates a pixel distance to a physical distance in the real world. We've also got another dot pattern. I can zoom in quite a bit on this one if we can focus there. So this is the sort of dot pattern that's used for BOSS, and the purpose of this one is so it can sit on top of the heater over here. It can sit in there in the same plane as the PIV, so it just sits in place, and its height and things can be, and position can be adjusted. In addition to that, we've got this one. The idea of this is a magnet in here, and so a ruler could be sat there and positioned against the surface, and the reason for that is this surface is actually quite big to try and measure in one go, and so if we were imaging from the top here, we'd get so far down, and then we would have to start another frame and image there and move down and so on. It's actually done in 4 parts, and we need to be able to tie those together, and one way of knowing whereabouts you are on the heater in general is to use a ruler or something like that. And finally, I've got 2 things here which I use to hold thermocouples, so the green bits are the thermocouples, and this is to perform some calibration for the temperature measurements of the surface. And similarly, these parts, they're actually metal straws, can be inserted into here to perform calibration of a fluid in an area here. And that was actually useful for a different technique called laser-induced fluorescence, or LIF. And you can see here that sometimes, in general, it's better to try and use like 3D printed components, like this is 3D printed, this, all of this, and this, etc. And sometimes it's necessary to machine them, and wherever you can, you should try and use stainless steel because it doesn't rust. And so some of the things that I've got to do very first is clean out the bottom of the tank, which is filled with bits of rust, dust from the air, and leftover seeding particles, and just general detritus that has gathered in the experiment over time, despite the top being covered. So zooming out a bit further, we can see a few more components of interest. So the laser cavities themselves are down here. So there's 2 laser cavities. One will fire at one point in time, another one will fire at a set point in time later, which is controlled by the user. The laser beams that come out go up this tube, along here, and into that laser head, which using the light sheet, which is all ready to go. Of course, we've already got the cameras, we've already seen cameras over here as well. In addition to the laser, there's also the laser power supply, and that's providing power to the flash lamps that are actually driving the laser inside. And on top of this thing over here, there's some manual controls for controlling that power supply and what the laser is doing. So it can either be controlled automatically by the software when you're trying to gather data, but when you're setting up and things, you can swap this all onto internal timing and internal modes, and you can turn the power down and try and figure out where the laser's going and get it orientated and things like that. The PIV computer, so the thing that's running the show and gathering, timing the firing of the laser, timing the explosion of the cameras, sat down here, and this is what is gathering the PIV data and also performing the measurements thereafter. It's also the thing that's whirring in the background, it's got very noisy fans. Next to this, we've got another power supply and controller, and this is for the translation stages. So here there's actually 3 translation stages. There's a translation stage here, which moves the cameras up and down, and also will move the laser up and down to be able to scan automatically and gather data at different locations. Also underneath, you may not be able to see, there are 2 more joined together translation stages for moving this whole assembly backwards and forwards. And you can have 4 independent translation stages depending on what type of setup you want, but this is what was suitable for me. Coming around a bit further, so far right we've got an aquarium cooler or a chiller unit. And the idea with this is to remove heat from the reservoir to maintain a constant temperature condition in the reservoir, and so the cooling loops that are here are being chilled by this cooler over here and some associated pipeline which is running around the back. Finally, there's some other bits that we won't be able to see very often from there, but just at the very back here there are some power supply units you probably can't see, and then some fine-tuned resistors in a box to the side here, a peristaltic pump for injecting or extracting water with seeding in it, and the very last bit, 2 bits, are at the back here, sat behind this thing, is a data acquisition system which is connected to a load of thermocouples and sensors in the experiment, and they are that in turn is connected to a computer that's behind this monitor, which is at the back here, which is taking in all of that data, which is monitoring the conditions of the experiment. And finally, the very last thing to mention is this, which is how sealing particles are introduced into the water. Roughly, what happens is the pump that's sat behind this thing is switched on, and the experiment is up to temperature. You draw some water out from the experiment, draw it into the seeding tank at the top here, and then introduce some seeding powder into here, mix it around, and get it quite concentrated before it can then be reintroduced back into the tank. Now, that can either be done by the pump, just simply putting that fluid back in, but also this can be gravity fed down the back and distributed in here as well in a number of different ways. So that's how the seeding material gets introduced during the experiment, in addition to just simply pouring some on top, which is an option as well. What I'm going to do first then is break down some of the experiment to try and get rid of some of the rubbish and gunk out of the bottom here, which will mean taking off this side panel, removing some of the structure over here to be able to gain access and give it a wipe down. Once that's done, I'll be refilling the water tank, and there's a water tank up here on top of that structure there. If I block out the light, you might be able to see it. So the tank there, and that's actually running around here, coming across, and then coming down to a pump which is at the back here, and at the minute it's set on very low, but that tank's getting a little bit low, and this pump goes into the chiller and is what's supplying coolant around all of these pipes. So actually the cooling system has quite a large inventory of water. That tank is just filled with filtered tap water, and that filtering is done just to the side here. So you might be able to see there's some filters there, which is how water is introduced into the system, or one of the ways that water is introduced. So I'll get on and do all of this. We'll do a bit of a time lapse of that process, and then I can show doing some measurements and getting set up after that.
So whilst I'm busy cleaning, I thought I'd just mention some of the other components, like the Thor Labs science desk that you can see there, which has got a breadboard on it, which has got loads of holes in a set pattern, threaded holes, onto which you can mount a whole host of different accessories and components. But you can also see there's quite a few different linear profiling or X95 profiles, which are holding the cameras and all the other structures around there. Generally, these are called optomechanical components.
Okay, so you can see things are looking a bit cleaner in there now. I just used some ferroliquid, so a mild detergent, to clean some of the surfaces, and it looked pretty terrible before, but most of it comes off really quite easily. This mark that you can see here, by the way, is the adhesive from the back of some duct tape, which doesn't come off very easily, unfortunately. But everything else inside is now pretty clean. So the next task is to try and fill this thing up. Now, doing that on your own might sound kind of tricky, but it's actually pretty easy. So the return feed comes in and is sat higher than the base of the water. So when, at the moment, that pump that drives this whole system has been wound right down to 120 RPM, so it's quieter for recording. But what I'll do now is speed this thing back up so I can hear it, and then I'm going to introduce some additional water flow. There's actually a couple of ways that I can do this, but I'm drawing the water in from a tap, so it comes in down this yellow pipe here, goes through the filters, and then it can go into any two directions. So at the minute it's coming down here, which is feeding the hose pipe, which is how I've just filled the tank, but it can also be diverted into the other loop, which will then start to add coolant to that system as a whole. And so I'm going to be diverting it until I can't hear the water dropping back in that reservoir. So I'll be listening for that reaching the top there, and as soon as it is, I will stop. I'll shut off the flow, and it will be full enough. It doesn't have to be totally full, just it does lose water gradually over time. It's good to replace it. So that's what I'm going to do next. When you leave the pump for a period of time, if it goes completely off, when you switch it back on, it will go through a 4-stage degassing sequence, which essentially runs the pump backwards and forwards to try and dislodge locked air, which tends to gather actually around the impeller, and eject that from the system. And once it does that process, it will go to the lowest speed, and you can wind it all the way up to 360 RPM. When it's been left for a little while, the controls will become locked, and to unlock them you need to press and hold this button and this button together until you see an open gate, like so. When that goes off the screen, there's some up and down buttons here. We can just press the up button and up it goes. The minute this is in RPM, you might be able to hear this in the background perhaps now, starting to make a bit of noise. So this is in RPM, but we can also see in other units as well. So times 10 RPM. This is in meters of head. We've got meters cubed per hour, 0.3. That's kind of typical for this setup, sometimes a little bit lower. And then the power consumption as well, but I tend to leave it on RPM and it'll be left like so. Now, my preferred method for filling the tank in the background is actually to take off one of these sections and just use the hose as I did to fill the reservoir of the experiment. So this pipe actually is coming up from the chiller unit underneath. So these are all the feeds that go out to the different cooling loops, and then this is all the returns being gathered together in this manifold, and this is what goes down the back and comes up this pipework on the left hand side. So you can actually take any of these out to fill the system, and actually this is my preferred way because it also clears some airlocks if you get any in the system. The only downside is it tends to get a little bit of water here and there. So on the end of each of the pipes is an aqua stop, which means that you can leave pressure in the line and it will close a valve automatically, but it's not perfect. This is meant for a garden really, rather than an experiment, but it's good enough. So the way that I do this is just to close the tap there. So that will be closed on that valve, and if I take this one off there'll be a little bit of water and then the system will shut this one here. So that's what this is for. Yeah, here we go. So just a little dribble and that's it. Yeah, little dribble. So nothing to really write home about there. You can try and tuck it in so it's pointing upwards, and then it won't dribble all over the place the rest of the day. So we take the top off here. This is usually full of water when you've filled up the reservoir. So I'll just take this off and empty it into a bucket by pulling the trigger. Okay, and we've now got this one which is being fed from the mains, but it's currently switched off by a valve, closed off by a valve just down here. So I can plug it in. Okay, it's plugged in. I can open the valve. Check to see how much water is getting lost outside, and then you should hear a difference now as I empty it into the system. And so now mains water is being fed into the system, adding additional water to the reservoir, filling it up as we go. So I wanted to just give you a bit of idea what's going on over here. The water from the mains is coming in through here into the filters, and this is a back-to-back connector, so a double male connector to join the two hoses together. And I've switched off the mains water supply now at the tap, and so this hose, which was connected, comes along here through all of this hose pipe. It is now not doing anything, there's nothing coming out. The diverting valve here, the selector valve here, is selecting where this flow that comes down is going. It can either go that way into the experiment, which would be normal, or it can come this way through this pipework. It can't go back through the filters because there's a non-return valve here, and so it has to go through this hose pipe and will come out to here. The idea is that you can connect this hose to this hose and use the pump to drain down the whole water system straight into the sink to make it a bit easier to clean the system after use. So that's what I'll be doing at the end of the video. So just to show that in action, currently selected so that the water's going into the experiment, nothing coming out of, or just the dribble coming out of here. And if I select it across, the RPM value or the flow measurement on here reduces to what should be essentially 0. It's just churning the water there, and then this will out and can be used to drain the system down. I'm just setting it back, ready to take some measurements. So we're about to start using the PIV system, and this seems like as good a time as any to talk about some of the safety aspects of working around lasers. Most PIV systems use lasers for illumination. Some use LEDs, but most use lasers. And the type of laser that's used is a class 4 laser, which is the most dangerous type of laser. Essentially what that means is if you take a direct strike from a class 4 laser beam to the eye or to the skin, you will be permanently blinded or receive permanent damage to your sight or to your skin in the form of burns and things like that. So there's something we have to work quite carefully around, and of course there's various safety things in place to do that. It all starts with how you approach the situation and working in a safe manner. And the very first thing that we can do is when we're in the lab, you avoid having reflective surfaces on your person. So my hands are currently clear, apart from I've actually got a silicone wedding ring, but if you have any other jewellery that's shiny, you should take that off. So I've taken off my watch, I've taken off my pass with the keys on, and that's all left to the side. Next you'll have some laser safety goggles, and these particular goggles will be rated to the wavelength of laser light that you use. So the type of laser that we use is a neodymium YAG laser, which actually inside the cavities emits in the infrared, but when that's joined and comes out of the laser itself, what we see is a green light, which is 532 nanometers. So these goggles are tuned to provide protection and filtering to a certain standard for 532. Actually, these cover a variety of different ranges, and you can always find this information and these codes on here is what dictates the various ranges. So you can see there we've got 315 to 534, for example, that's the nanometer range, and LB5 is dictating the level of protection or filtering, where the higher number is the better number. So we've got two here. These are the ones I'm going to be wearing, and I'll be holding this occasionally in front of the camera lens. If you just look through, obviously it turns the whole world orange, but what's quite good about these is they're sometimes called alignment goggles. You can actually see a very small amount of the laser light is allowed through, and that's quite handy with the task we're going to do next, which is aligning the laser plane to our plane of interest, the plane where we want to take the measurements. So in keeping with the safety theme, all laser labs should stop any stray emissions. So here is a curtain which spans the entire region. There's no breaks in that curtain, and the building that we're in has no windows, so only the people inside of this controlled area, sometimes called a laser controlled area, are likely to receive any emission. And so what we kind of do is stop at this ingress point anyone who hasn't been formally briefed on the risks that they're about to face, and obviously they can't use the system themselves. In addition to this, in case someone just happens to wander in, almost all labs will use some sort of interlock system, and that's what these things are here. So the interlocks are a way of breaking this system, or breaking an electrical connection in the event that someone inadvertently comes in. So if someone were to come in now, this will sense that the curtain has been opened. That ties in with this panel over here, which is the interlock system, and at the moment there's a number of interlocks, and all of them are showing as closed. It's essentially a switch. If I open this one again, so it's now open, we can see that the interlocks have now been broken, and A and B refer to the two switch measurements on this same interlock, and there's a number of those around the building. Without these interlocks being clear, we can't arm the laser, it won't work. Yeah. Well, we can't switch the laser on, it simply won't work. Whereas if we close the interlock, the light is illuminated, we're told that safety is okay, and we could now arm the laser. All that's really doing is sending a signal to the laser power supply to say that, okay, the external interlock system says that things are safe. So the laser power supply then, it's now switched on. It's kind of noisy, so I'll have to do this from afar. But if I just quickly push in here, you'll see there are some switches here and here for the different laser cavities, and these are controlling whether the trigger signal to fire the laser comes via these wires, which connect back to the computer, or whether they come from this control system at the top here. And I'll just zoom in quickly and you'll see they're set to internal trigger. So, internal trigger, internal trigger. What that means is we can control the system using this control board, and if we want to fire the laser, we need to firstly switch the system on, which is what's done here, and the system won't fire. I could try and tell it to turn the laser on, it won't do that. I can open and close the shutter, which is kind of like a door that allows the light to go through, but nothing will be emitted, and when there is an emission, this light will come on. To fire the laser, the pump must be on. The pump, as you can hear, is now on, and all of the settings for firing are set by this. So this is the repetition rate, so the frequency of the pulses. This is the power for each individual cavity, so laser 1, laser 2, and finally this is an attenuator, which essentially sits right at the very ends of the two laser cavities at the back here, and there's some steering optics in the middle. One of the final things is an attenuator in there, which kind of reduces the amount of light that's allowed to go through, provides some filtering. And so we can set that, and typically when you start the laser for the very first time, you want to reduce the attenuator right down. And so just do that by turning this to the bottom, and you can see there that it's reading 0, 0, that's in percent. And we can go up, and we're now at, so just about 13%, something like that. Okay, we're now ready to turn the laser on, so the laser will be now firing, but it's not emitting anything because the shutter is closed. So we'll hear the laser fire in a moment. There it goes. You can also see there's some lights down here for the emission. And if we fire, before actually letting any light loose, we say firing and emit and stop. Okay. And then you can turn the laser off. So the purpose of saying firing is so anyone in the controlled area can put their goggles on before you have to fire. At the minute I'm the only person in the rig. Task now is to align the laser light sheet with the region of interest. So we can turn on the end here this optic, which will change the orientation of that light sheet, and we want to get that in line here. Now there's many ways that you could actually align that, but they pretty much all involve suspending something from the top here, usually a calibration target or something, and aligning the light sheet with this edge of that calibration target. Whenever the system's not in use, there'll be a cap left on here, so that if we want to see what's going on, we have to take the cap off first. Okay, there it is, just a piece of metal. And the other thing we've got here is this is a focusing ring, and that will change sort of the laser waist, which is where the laser will come out and converge. It's like this. It will converge to the thinnest point, and we can use the focus to control where that thinnest point is if we've got a really strict measurement that we need to take. But the bit at the front here is used for steering the light sheet. So what we need to do is get the laser firing and aligned, and we'll see what we can see. You may be able to see a bit more than me on the camera, just because of how the camera works on how this is being recorded. So we'll switch the laser on again, system on, pump on, laser on, firing, open the shutter, wait for the laser to start firing. Okay, so you should be able to see the laser appear here. From what I can see, it looks like on the screen it looks like it's going on and off. It's not, it's just the recording rate of the camera is different to the firing rate of the laser. So I can change the repetition rate somewhat, and maybe it will stay on all the time. Okay, so I'm slowing it down. You might be able to hear that. Okay, there we go. That'll have to do. Now if we want, there's two things now. The light is going to be coming in this way, and it will be reflecting back. Now, because I've used this system before, I know that that's the case, but if I didn't know where the reflections were going, It's quite useful, particularly for these goggles and a green light, a green laser light, to have something like this. It's just an orange piece of post-it notes on a stick, and anything that's orange you can see through these goggles, and so I can check to see if there's any reflections. And you see that's a primary reflection there, so the laser sheet is going all the way across, reflecting off the heated surface and coming back here. So we want to avoid sticking our face or sticking our anything really in the way there, and this is how you can detect them before you put your squishy skin in place. So you want to try and align where this light sheet is, and one of the things that you could do is just put something like this in by the surface and align against something orange, because then you can see it through the goggles. And I'll try and show you what that looks like. I'll just cover up the lens so you're now seeing kind of how I see it. And so here is the orange target, and if we just put it there, you should be able to see the laser flashing on there. It's quite clear to me where that is. Okay, so I'm going to get that aligned now, and we'll carry on from there. Just doing this alignment, that the power of lasers themselves are actually quite high, that's full power, and using the attenuator, which is about 20% of the full power, is being allowed through. So you would normally start at 10, 20%, up to 30%, whilst aligning the laser, as it provides enough light that you can see it, but less of a hazard to yourself, both from reflections and from direct strikes from the laser beam. Another general rule of thumb is this is where the laser beam is coming out, and right as it comes out of the lens, it's effectively still a beam, and it's at that point that it is its most dangerous. So try and avoid looking where the beam is, don't look at there, and as it starts to diverge like this and spread out, the intensity of the light is not so strong. However, it is still sufficient when it's at full power to provide a genuine risk, and of course you should never take off your goggles. There's really no need when you've got alignment goggles like these, and you can figure out where the various reflections are with something so simple as that. And make sure you don't, for example, put your computer in the location with a direct strike. If for no other reason, then it will give you a really bad headache even through the goggles. You might be able to see now that I've introduced a calibration target in the plane of interest. And this is another calibration target. It looks just like this. The one in there is a little bit smaller, but it's a dot pattern. This particular target is on 2 levels, which is useful for stereoscopic calibration, in addition to planar calibration, which is actually what's being performed here. So the calibration process can actually be done at any time. It doesn't have to be done before an experiment, and it could be necessary to do it at several points and at several different conditions. For example, at a set temperature of water inside the reservoir was crucial for this case. However, it's quite useful to do this when there's no sealing particles or debris in the water itself. It's just water in there now, so doesn't pose too much of a hazard. So the purpose of this calibration is actually several-fold. So the first thing that we can do, as described moments ago, was we can use this to calibrate or to align the laser to get it in the correct orientation against this target. Similarly, we can align this calibration target so it's not sat to one side or another with respect to how the laser is coming in. And finally, we can use this to calibrate the cameras. So first of all, we want to make sure the cameras are in focus, and then we want to perform an optical calibration, which means we know from where the camera is, we relate the distance in pixels to a real life distance in terms of like millimeters or something like that. And to do that, we're going to use the PIV software. So this will obviously be different for different softwares and different versions perhaps of the same software. But first of all, we need to take the dust covers off the lenses and I tend to leave the cameras out slightly. We'll just use the one camera, so I've switched the camera on, and we can now swap over to the PIV software. As a final note, the choice of calibration targets is kind of dependent on the size of the area that you're trying to measure. Similarly, it's also dependent on the lens that's used, which equally depends on the area that you're trying to image. So this particular system is quite high definition in terms of spatial definition, and so we're using a relatively small target and a relatively large lens. So the first step to calibrate the cameras is to get the image in focus. So what I've got on the screen here is an output from both cameras. So if I switch to the live mode, you can see that the counts are bouncing up and down as the noise is, as the ambient light fluctuates. At the moment there are filters on the lenses, and so it's appropriate to use an exposure of around 10,000 milliseconds. If we didn't have any filters on the lenses, you wouldn't need such a long exposure. But all we need to do is to be able to get a reasonably high contrast image here from the two cameras. And I can swap between them like so. You can see that one of them is pretty reasonably in focus and the other one is completely out of focus, and that's because it's focused on the rear of the experiment and it's focused on the target. So what I want to do is bring that one into focus, and I of course will always get the wrong one, and so what I'm doing is just rotating the focus on the lens, watching the screen simultaneously, trying to bring this into focus. This particular bit of software has a drop down which enables you to see at the top here roughly how well the focus is being performed. It's also got the dynamic range there, which tells you the depth, the bit depth of the image that's being used of the total available. So because there's not much light going in, there's not very much dynamic range being used. Anyway, we're looking to get it in the sort of ballpark for focus, which is around about there to my eye. Your eyes are often pretty good, so it's not necessary to rely on anything automated. So if you're looking at a particularly oblique angle, or if you're not looking straight on, you might find that one part of the target is in focus and the other part isn't. And that's where you could use something like this, which is a Scheinflug adapter, and that enables the lens to be slightly rotated with respect to the camera. So this would fit in between the camera and the lens, and enables you to bring into focus something that is not in the same plane, or not coplanar, with the imaging sensor. But that isn't necessary in this particular case. So the assumption now is that the optical alignment has been performed, and that varies with different types of software or different versions of the same software, so I'm not going to show that process, just through the manual of the appropriate software. But the very next step then is to bring fluid the seeding particles into focus, because we've kind of got close with the focus, but now we need to make sure that the actual particles that we're using are correctly in focus when they're being illuminated by the laser light sheet. Now there are some cases where you might want to avoid and where you want to intentionally introduce a small amount of blur, but we're not going to worry about those right now. That's for something called peak locking, but we're not going to use that technique. As a general rule, you want them to be in focus. So the way that you do that, quite simply, is to introduce some particles. We're just going to sprinkle some onto the top, and then they're gradually, very gradually, going to sink down. Now, the particles are obviously supposed to be neutrally buoyant, but in practice there's always going to be a slight difference, and as it happens, the particles will have a sinking rate in the sort of the micrometers per second. So it takes quite a long time for particles to make their way down. So I'll probably inject some near to the surface and into the field of view, just so we can see what's going on. Once we can see some particles on the screen, we can then refine that focus, and at that point we're ready to start taking some measurements. So I've introduced some particles in here, and you can see they're kind of sat on the top. One of the things you can do is to just mix them in like I'm doing now, which will start to disperse them. These particles are absolutely tiny. It looks like you're introducing flour or a powder in here, so they do tend to clump a little bit. It is actually better to produce a concentrate and then inject the concentrate in rather than just drop them on the top like this. But I was just hoping to get a few in there to get us going. So the type of particles that we've got here are a polystyrene particle which is coated with rhodamine, which is why it looks pink. And the purpose of using this sort of particle is that the rhodamine will absorb some of the incident laser light and then will emit that laser light out at a different wavelength. And why that's important is near to a surface you get a massive amount of reflection of the laser light, the 532 nanometer green light near to the surface, to the point that it completely obscures the reflections from the seeding particles. And one way to get around that is to have an emission from the seeding particles in a totally different wavelength. So actually we'll be emitting some sort of like yellowy orange colour rather than green. And then by putting appropriate filters on the cameras, we can make sure we can preferentially see these particles with respect to the background. And it works very well. It's a very successful approach. Okay, we'll see how we're doing now. So I'm going to be firing the laser. I'm also going to increase the power for the laser. So I happen to know for these types of particles, we're going to need the entire power of the laser to be able to see them particularly well. So I'm going to open up the attenuator fully to 100%. Which takes a little while, it's quite a slow dial. Okay, 100%. I'm going to bring the laser on, and we're going to have a look and see what is visible when the laser's on. So bring the laser on, and firing. Oh, hold on. Nope, we need to swap to the other. We need to swap the triggers. So we're triggering using the computer. Okay, let's try that again. Laser on. Firing. So that's now controlled by the computer. If we go to recording in this particular software, it will start firing when the computer tells it to. And we're going to have to reduce the exposure down from the 10,000. We'll go now for about 100 milliseconds as for the exposure on both lenses. And we should be able to see something. So let's have a look. So the laser's firing there, and let's see what the cameras can see. So we've got particles moving. You can probably see them on the camera as well, directly in the flow. Maybe not. Let's just try putting. So what you're probably seeing on the camera right now is the green light, and if we cover it over, no, you probably can't see it there. But what I can now see is particles moving around as a bit of a swirl, and this is as a result of the flow from me spinning, trying to agitate the flow there. What we can now do is zoom in on these particle images to see if they're in focus, particularly near to the surface, which is over here. And you can see that they appear slightly out of focus, and so just as before, the task is to bring them into focus. And you're obliged to go the wrong way before you go the right way. Very small adjustments now are necessary. What you're looking for, so if we go a bit out of focus, I'm looking on camera, what we're looking for is, let's bring it out of focus. When they're out of focus, you produce these things which are called airy rings. And so if we find those and then gradually get rid of them, there's a little bit of a delay between the adjustment you make and what you see on the screen. And really what we're looking for is a nice compromise. There's always going to be some particles that are out of focus, but we want to try and get the vast majority in. A little bit more. Okay. Now what we're really looking for is for the particles to take up a certain size. It's a little bit difficult to do this when we have all of this information or all of this image live. So if we take a single image now, okay, so we've got a single image, we can now zoom in and see how many pixels these particles are occupying. And we've got a minimum requirement here. We want them to take up at least 3 by 3 pixels. Bigger is okay, smaller is not okay, because noise often occupies just a single pixel as well. So we want to have an obvious particle image. Some of the hardest parts to taking the measurement are actually to do with getting appropriate seeding in the region that you want. At the minute the seeding is kind of uniform across this geometry, but as soon as we switch the heater on, what we'll see is a region near to the surface firstly becomes refracted, blurred and lost from view, but even if we could correct that, we would find that it's quite difficult to get seeding particles very, very close to a surface. And actually the way I approach that in this experiment is to seed from below very near to the surface by observing where the near wall fluid was being drawn from. Now that strategy won't work everywhere, but it did work here. So now let's assume that we were going to take some images, take some measurements properly. What we would do is firstly made sure we've appropriately seeded the geometry however we needed to, and we've given the system time to sort of homogenize and distribute the seeding particles. We don't want a clump of seeding particles here or there, we want them kind of distributed everywhere. We can then choose some of our timing parameters, so this is how fast you're making recordings. Obviously if you've got a very fast moving flow, you need to record quite quickly, whereas if you've got a slow moving flow, you've got quite a few more options about how you cover the range of interest. And finally we've got the duration. There's quite a few other recording parameters in here that I'm not really mentioning, but we've got the duration. And you would choose that to ensure that you build up the correct statistics or that you measure the correct phenomena of interest. It's very problem dependent, so I can't really give a general advice on this, but you need to make sure you're observing for a long enough period. So in this case, it's going to record 100 images at 15 Hertz, which is the fastest this laser goes, and using these parameters up here, so the laser's on pretty much full blast and the camera's at 100 milliseconds. And what I'm going to do during these 100 images is try and nip across and switch on the power supplies. Maybe I'll make it a little bit longer, and we'll do it as a time duration. I'll give myself 20 seconds, okay, 300 images, and we'll reduce the recording rate down to just 10 Hertz, so we should still capture most of the information. That's primarily so I can get across and turn the heaters on. Okay. So all we need to do now is ensure that the laser will come on, 10 Hertz, and then hit record, and it will begin recording immediately. Okay, here we go. Let's switch some heaters on. I'm going to record another set straight away, so recording again. You can actually turn off this live view if you want to save on some of the computing performance. But we seem to be doing okay. So we recorded some data there. It's not going to be very good data, to be fair, because we've still got quite a lot of particles settling. There's quite a lot of motion in the bulk region, of the quiescent region, that's going to be affecting the quality of our results. So you can see there's some of these pretty large clumps of particles. They're pretty heavy. If we wait for a little while, they'll tend to make their way down to the bottom and simply fall out of view. They won't become a problem later on. Now we can review what we've recorded. So this is the recording. You might be able to see that very near to the surface we've got flow, and you can see the particles moving up here. You might also be able to see some streaking where the particle images are being refracted. See if we can make this a little bit bigger. So you can see the particles making their way up here, and we've got this blurring occurring near to the surface, and those striations, or the elongation there, is very characteristic of refraction occurring near to the surface. So it doesn't take much at all for this to occur. So that's our raw PIV data, and what we would now do is run this through various filters and through the PIV algorithm to return a set of velocity vectors from this raw data. So as hopefully you've seen, actually taking the measurements is really, really easy. You just simply set the time and duration that you want, and you get the results that you need. The hard part of this is specifying what those things are, how long you need to run the duration for, and and what sort of exposure, and looking at all of the different recording parameters, and simply specifying the experiment in the first place. Those are the harder tasks. Taking the measurements is pretty easy. So the next task is going to be to drain the experiment down and disassemble it. I'm not even going to show part of that process, but the question becomes, what do you do with the waste particles? Well, if you can recover them, that would be great, because they're quite expensive. And so if we could extract these out of the water, that would be the ideal solution. The way that you can do that, as you might be able to see, is they all tend to sink towards the bottom. And so if you can sort of funnel them into the same place, scoop them back out, you can then reuse them in the future. One of the ways that I've done this is to draw them in at the bottom and try and pump them into the seeding tank and leave them in the seeding tank, where even if the water gets evaporated off over time, I can just replace the water and I've got a ready supply of seeding particles ready to go. If you must dispose of them, exactly how you dispose of them depends on the material safety data sheet for the particles that you are using. It's not one size fits all. The particles can be made of all sorts of different things. Generally though, if it's got some sort of coating, or if you introduce any dyes into the water, you're probably going to have to use a specialist disposal process, whereas if it's just typical normal uncoated particles, you can usually get rid of those without specialist disposal by putting them down a drain or down the toilet or something like that, but definitely not into the outside water supply. And this is guidance maybe only for the UK. How it works abroad will differ. So the way that I do this is to simply drain down. I've got a pipe off the back here, and I will drain that into an appropriate container, and I've got a tap that sits and draws from the bottom of the experiment. One of the things that I would encourage, and I wish I had done, is to have a raised section in the middle of my experiment, such that all of the particles that I've I'm not using will then fall into the bottom. I kind of wish they would have gone to the sides and left a clear section for me to provide illumination through. But I didn't do that, and in the future that's something that I'll incorporate into my designs. Okay, so the system has now been drained down, cleaned out and disassembled. It should be that if anyone reintroduces using the translation stages in future, there's no collisions likely, which was a worry before, and it will require some amount of assembly before it can be used again, but it's now ready to either be disposed of or to be put into storage. And what that really means is putting caps over anything that's dangerous in terms of like the laser, but also protecting lenses and things from dirt ingress and dust buildup and stuff like that. The last step that's happening as we speak is just the large water storage is being drained down. That's just going straight into the sink, and as soon as that's done, this should be all completely finished. And so that's the end of that.